François.
First one, yeah.
This one is François?
Yeah.
Good. It's PPTX.
Yeah, download.
Good.
Yeah. Shall I keep this inside this folder?
You are live, by the way.
Okay, it works.
So what your screen is being shared. 2 people watching. One is
Oh,
me.
but because Luke already shared link at some point, right?
One is me.
The other one is YouTube. Somebody.
Okay, so slides are okay. I can go down and see this play. And I hope that this works. Should I click start recording too?
Yes.
Who starts? I start.
Okay, I don't know. You
Juste ce logo là. Ok.
Hello. Test. Yeah. It's inside this PC. You want to try this? See that?
Maybe leave it.
Yeah. Do I need to open and test? No. Screen sharing.
But no, it's fine. It's screen to everybody. So.
Yeah.
Ça stream.
Seems to work. Question will not work. How does it work?
Play button.
Where's the play button? Yeah, fine. Oh, cool. Is it like
No.
Shift Enter, Apple Enter, Windows Enter?
No, start automatically.
No.
In sequence.
Why you? Don't change that, okay?
Okay.
Just everything is fine.
Okay.
So I just want to play. I forgot how you play things from here.
Last one.
Sorry, this
It's
one.
actually seen in the live.
Yeah, cool. That seems to be fine.
Yeah. Okay. Who starts this? You start.
I don't know.
I do start.
Okay.
Ça marche sur réseau ou pas? Non, c'est la meilleure.
No, lecture mode.
Djibouti, I have a big issue. Il est dans tes spots. I can't get any internet.
You can connect to
TCD
TCD
guys.
No, TCD gas is 5 megabits long. I can type that. Should be fine.
Give me one.
YZSJ SJZ. Password is 333667.
Je l'avais laissé. C'est avec eux. Is it possible?
Yeah, through YKR. KR. Yeah.
Je vais juste marcher ici. Je te le file. Ce sera là dans 15 secondes. It's hard. It's hard.
You're good with the internet now, right?
C'est good? I'm good. C'est bon? T'as reçu?
Yes.
Yeah.
It's
Yes.
recording and live, both
Yes.
good, all good.
Fully artistic, infinite depth. And some free advertisement for OBS. That's open source, right?
Yeah, so it's all good.
Yeah, of course. They're friends, almost.
So you send to yourself here.
Fast mail, 15 secondes.
Is it sent here? It's already downloaded. It's pasted there too.
Here?
Yeah, FFmpeg VDD.
No, it's a PowerPoint.
Yeah.
Okay, so why don't I have it?
Did it send from your PC?
Putain.
Oh yeah. Oh, just waiting for the intros like that.
Yes, of course. Okay, I'm good. It's live?
Turn on projector.
It's live?
Yes. Line, can you even change the lights?
Oh.
Make them more.
Oh, that's here. I could do that here.
No, well, yeah.
How do you want function?
Comment ça va plein écran ce truc là? How do you make it full screen?
View. Full screen. Yeah, good, right?
Good morning.
Just follow my.
Don't.
You want, you can use.
Yeah, I don't need. Hello? Non, c'est pas ça. Hello? 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 Does it work? Good morning, everyone. Well, I'm surprised to see so many of you in the morning. To be honest, I'm a bit late. I'm sorry. Some broadcasting issue for that. So, the usual talk in the morning. Welcome to VDD 2023. It's been actually 4 years. Yes. It's been 4 years that we met in Tokyo, right? And we tried to do 2 VDD since, and we failed because some horrible people put a virus on our planet. So I'm happy that all of you are around. There is a lot of people who've never been to VDD, almost more than 1/3, 40%. That is quite impressive. So you have to know that VDD is a bit weird. That's normal. If we wanted to be a normal corporate or Linux Foundation-like conference, we would do that. It's not, right? It's free. We pay for everything. So welcome to VDD. This conference is made cool because you're cool. If you don't make it cool, it's not cool, right? So remember, right? Like, make it cool. Yeah, that's me. I was young and beautiful. Now I'm old. Well, this was you. And some of you were, well, young and younger and less young and less young, right? Again, code of conduct applies. Like, I've had to say that. I've had to kick only one butt in all VDD conferences. Like, let's not be two. And I'm not nice, right? Like, I know I joke, but like, you know what to not do, so don't do it, right? Thank you to Trinity College Dublin. Thank you mostly to Anil, and also thank a special thank to vBooty, right? Because like this day, this VDD could be called vBooty Developer Days, right? I complain every time that people don't move their ass to do anything, and well, that's a counterexample. VDD 2023, thanks to vBooty. It's also sponsored by Mux. Mux is a nice company. They hire people, they organize DMux, and they are the only one actually sponsoring us with video labs. What are we doing this morning? The usual clever talks, and more clever talks. Then we split in two. We'll go upstairs. There will be an AV1 discussion in parallel to a VLC discussion, and then we will swap. There will be a FFmpeg discussion on the AV1 room, and a VLC mobile, right? So that's going to be 2 hours, or more, right? We could take 2 hours and a half, and so on. We have a break in the morning with coffee to help you for your headache. After, of course, a codec talk, right? There is a dinner tonight. Everything is on the website, on the wiki. You have all the information. Tomorrow we have another clever talk about the tool chain, and then we have lighting talks. I think we still have some space for lighting talks, so please submit them. And well, right, like let me remind you that this is an unconference, so like you can do other things, right? Like actually hack on some things because like you have a few Kodi people and you have a few MPV people, or you have people who care about HDR, which is a subgroup of weird people. Then you have extra rooms, right? You can see it's a Saturday. There is no one in the university because universities don't work on Saturdays. So go there, right? This will be open the whole 2 days. We have 3 rooms over upstairs. Upstairs is level floor 3, because this one is 2 for no reason. Like normal horrible people, they don't start at 0, they start at 1 on the ground, and we are on the ground and we're already at 2. Don't ask. You're part of the VideoLAN community, even if you don't like it. It's forced. Like seriously, it's the open source multimedia open source community. VideoLAN is a lot more than VLC. VLC developers are in minority at VDD for a long time. There is probably more FFmpeg or people than VLC. That's okay. VideoLAN is not here just for VLC. VideoLAN is for all open source multimedia projects. Have fun. And if you don't have fun, that's your fault. I hope you had fun yesterday. Right? Some of you did. Some of you did weird things. yeah, well, that was a joke, the priest part of the code, right? Like some people took it way too much. And of course, there is a mummy, right? So the result for the treasure hunt of yesterday was, will be tonight. Everyone who came to me and say, oh, your questions were ambiguous. Yes, that's the point, right? And for example, there were 0 fish, not 13. Okay. And now I'm going to let someone way more clever than me speak.
No way.
How do I do that? That works? Wow.
Yeah, it works.
Amazing.
All right. Good morning, everybody. My name is François Pitié, and I have the pleasure on behalf of the SIG Media Research Group to welcome you in Trinity College, Dublin. And yes, that's my name. I just wanted to take the opportunity to present to the group, and I'll be very quick, so that'll be all okay. So the research group was funded by Professor Anil Kokram, who was supposed to give the talk, but that's still there at the back here. And he knows how to delegate. That's very good. And so there's 3 academics, so myself, Anil, and Professor Naomi Hart. And yeah, we've been doing anything to do with image, video, and speech processing. And I just want, like a just very brief overview. This is how it started back in the 2000s when you guys were starting VideoLAN. We were doing this kind of stuff. So archiving was all the rage at the time. And so we had, this is the oldest film shot in Ireland on the left. I hope you can see that this is the original degraded video. And on the right, this is the result put together by John Squires over there, putting together a whole bunch of automated tools we designed to make that better, hopefully. And so what happened is, while we were working on that, Anil was approached by people from the movie post-production. And they found that very interesting because at the time, they were working on, so the people that, from the foundry, they were working on this movie called The Matrix. And so what happened is that they didn't know, they wanted to improve the way they were doing the frame interpolation they were using to be able to have these smooth camera moves. And so Anil wrote the algorithm for that, and he got a technical Oscar for that in 2007? Seven. I failed here. And so from that point on, we all started to write a whole bunch of tools for the movie post-production. They've all been used since 2007, really, or 2004. And then at that point, YouTube was interested in picture quality, and so hired Anil. And so Anil went there for 5 years, and then came back, and then we all started to do a bit of your kind of work on video transcoding. So you all know about Vibhuti, and well, he's doing a lot of work on HDR, per clip optimization, and so on. But we have a whole bunch of other work going on in video enhancement, so the kind of things you want to do to improve the result of the compressed video. And I just wanted to show you at the final video just an example of that. So this is a work from Darren Ramsuk, a PhD student here. And this is using neural nets, because of course we all do neural nets. And so on the left you have the compressed stream. And I'm afraid I forgot exactly what codec we use for that. Is it H.265? Yeah, it's 265. All right. And on the right, we have the post-processed version of that using his neural net system. And basically what's interesting here is that if you look at the PSNR, we're somehow degrading the whole thing, it seems so. But if you look at the VMAF, it's a lot better. And basically what Darren has done is a whole bunch of work to trying to have some kind of perceptual metric built into the neural net, so we can optimize our neural nets to produce better videos. All right, so that's it. So I just leave the floor. And again, thank you to Vibhuti and also to John Squires who both of them did a lot of work for the local organization.
How do I put that full screen? Yes. Even level later. Wow, we're getting better every year.
Nice. Okay, so for those of you who don't know me, I'm Anton Chernov. I've been working on FFmpeg and libav while it existed for a very long time, since like 2009 or so. These days I work with FFlabs, and I've been working on a project for the FFmpeg CLI, the command line tool, which is multi-threading. It's not really all about just multi-threading. I will say more about that later, but that is the marketable term. So, it is the most widely used transcoder on at least 2 planets. It is, seriously. It's very widely used. It uses the libraries from the FFmpeg project, libav codec, libav format, libav filter, and so on, to do almost everything. To demux, decode, filter, encode, mux, whatever you can think of. All the format-specific logic is in the libraries. So you might think that there's actually nothing interesting in there. It's a thin wrapper around the libraries. What's the big deal? But actually, it has like 200 options. It covers more use cases than any comparable tool that I know of. Way, way, way more. It is used on all scales. Single users, individual users use it to convert FLAC to an MP3, and giant corporations use it to run transcoding server farms and anything in between, and Mars rovers use it to record video and send it back to Earth. The scales at which it is used are just insane, and there is, for that reason, there's a lot more to it than just a simple wrapper. So it is quite a complex program, unlike what you might think. I will say a bit more about its history, and there will be a practical reason for it. So when the FFmpeg project started in roughly 2000, there was already FFmpeg.c in it. It had like 700 lines of code. There was no demuxing, there was no decoding. It could take raw YUV input, it could read PCM files, or it could grab from V4L or DevEnd or DevDSP. It could encode that, and if you had both, you could pick just one of those, but if you had both, it could mux. And at the time, that was quite a big deal. Interesting achievement. The man page boasts how it's hyper fast, and you can do like 300 by 200 encoding in real time on the machine of the day. So, yeah. But only a year later, we had this already. I wasn't there at the time. So Fabrice and the other people. We had multiple inputs. There was demuxing, there was decoding. We had multiple outputs. There was stream copying. There were no subtitles yet, but you could already build, in theory, things like these, and it had already 2,000 lines of code. I say in theory because, as far as I know, when I started working on this in like 2010, nobody actually understood how the map option works. Seriously. So the number of people who could actually build a processing pipeline like this back then was about 3. And I'm not exaggerating, but it was possible, and in theory, and you might think that this is almost what we have today. Almost, but not quite. As time went on, we got subtitles. The size doubled. In 2010, we got simple video filtering after AV filter was merged into mainline after a very long time. Then we got complex filter graphs. The laser stopped working. We got complex filter graphs, which are best compared to simple filter graphs. A simple filter graph is such that has exactly one input, exactly one output, and both are of the same type. So one video in, one video out, or audio. Complex filter graph is anything that is not that. So it can have multiple inputs, multiple outputs, different types, 0 inputs also. And we got support for that in 2012. That was me. That was a big change in this picture that you saw. We got some support for hardware acceleration. Back then, people didn't believe that it makes much sense in a transcoder because obviously hardware acceleration is something you do in a video player. Why would you ever use it in a transcoder? Nobody knew back then. Some people maybe know now. 3 years later, we got full hardware pipelines with Mark over there. Good job. From decoding to filtering to encoding, all the way through. Right now, we have 11,000 lines of code. It grew quite a bit. We got dynamic parameter changes. They are now normal and common. They used to be somehow not really supported, but now they can. We have an absurd number of options. Nobody can remember all of those, and I say that authoritatively because I can't. They interact in very non-trivial ways that very few people understand how, if you use the T option and the shortest option and complex filter graphs and 3 output files, how exactly will it work? Nobody knows. And now, so the general processing pipeline looks kind of like this. It's a bit similar. There are filters in the middle between decoders and encoders. We have subtitles. You can stream copy. You can have 0 inputs here, for example. You can use a filter graph that grabs from your screen and then it has 0 inputs, and so on. And you can make this arbitrarily complicated. And now, the critical question is, and why I'm talking about this at all, do you think that the actual code of FFmpeg *.c matches this? It's a trick question. No, it doesn't. Because the way this program actually works is that somebody in the year 2000 writes a simple transcoder, and then somebody wants a feature, and they just somehow add this feature on top. And then somebody adds some other feature on top. And then they build this kind of a thing, a blob, that matches sort of the architecture as it used to be 20 years ago, but it actually grew into something completely different. So a big problem was that FFmpeg.c was completely unmaintainable. And you couldn't really add major features to it. Like you could tweak things at the site, but adding anything substantial new to it was almost impossible. Like the complexity grows exponentially, so at some point you just cannot do it. So, so the goal of this project, which I started 2 years ago, I call it multi-threading, but the actual goal is bring code structure in alignment with the actual architecture. Threading is a part of it, but it is kind of almost a side effect of what we are getting. So one way I'm doing it, I'm making more explicitly object-oriented. There are more objects, and they behave more like actual objects than just like structs that you dump your data into, and then random pieces of code just randomly access and change that state. Now we have public and private states, which is a big deal. Some people don't believe me that this actually makes sense, but yes, it does. We have clearly defined interfaces, clearly defined responsibilities. Also, every major component is moved into its own thread, which has advantages. You would think it's just for speed, for performance, but also for me, the main advantage is actually enforced separation, because now before if some components access something it shouldn't, it's just ugly. With threads, it's a race. So there is like a very strong case for not doing that. But yeah, also in some cases, when your transcoding is not dominated by a single component, you can also get improved performance, which is important. But for me, mainly makes the code easier to understand, easier to maintain, easier to extend. To show you this also, what would actually happen is that when you describe to somebody what the tool does and how it works, the person gets this picture in their head and they say, well, obviously it should be written like this. Obviously the data flow should be that you have these nodes which are connected to pipelines and data flows downstream through these pipes. Obviously that's how it should work, and it doesn't. You would get things like decoders touching into muxers here, and you would get some kind of backwards teleportation of information, which is just completely impossible to understand or follow. So one of the goals of this project was to get rid of that as much as possible. It's not possible entirely, but to a great degree it is. So, as I said, it started in late 21. So far, 700 commits. It really depends what you count as a part of it, but I would say at least that. What we have currently upstream, we have demuxer threading, which was there for at least 10 years, but it wasn't enabled by default. Now it's not even just enabled by default, it's the only option. Now we have muxer threading, like for real. We have fake decoder threading upstream merged. But what I mean by fake is that there is a decoder thread, but the main thread gives it a packet and waits until it's done. So it's not really parallel, but it's like it's scaffolding on which the actual final result will be built. Along the way, we got some really nice things as sort of a side effect. Timestamps handling improvements. Previously, we would have some tests of row H264, where the output timestamps would start at 77. Why? Because now that is fixed after 20 years. We have frame duration handling all the way through, which is very nice, and we didn't have that for a long time. We have this very nice feature which is called opaque pass-through, which means that when the demuxer gives you a packet here, you can attach data to it, your own user ref counted data, and it flows all the way through, and you can then get it out here if all goes well. That used to be kind of maybe possible with a lot of effort and a lot of work, but now there are APIs that make it very simple, and FFmpeg.c actually uses that, and if you have your own program, you can use it, and I think it's very useful in some cases. So that was like a side effect, and we have these things which are called sync queues, which most people don't care about, but they make the output predictable in some cases where it wasn't before. And what is under development right now, fully threaded transcoding, it sort of works in my local branch. It's not yet entirely finished, but it works. I'm getting workable output. I'm actually getting some speed up also. Needs more tuning, needs more testing, but it should be there soon. In the future, what I would like to do, I would like to fully separate encoders from output streams. What happens right now is that in the code, encoders are a part of the muxer. They are embedded inside. So every encoder has to be a part of the muxer. And what sometimes you would want to have is standalone encoders that, for example, you have one encoder that sends its output to 2 muxers, or 3 muxers, or 55 muxers. Or maybe what you want is to take encoded output and loop it back to the decoder, and then feed it to a filter graph and say do metrics on it or something. If we had separate standalone encoders, separate standalone decoders as first-class objects that could be instantiated dynamically, for example, that would make some use cases possible that were not possible before. I would like to see dynamic pipelines at some point. So really at runtime, you spawn new inputs, new outputs, or you delete some old ones. This probably needs some scripting, maybe in Lua at some point. So those are the things I would maybe like to see at some point. Maybe we'll get there. Okay, thank you. Questions? Yep.
So, I like this design, by the way. It sounds a lot like how GStreamer used to be introduced. Is it inspired or meant to be like that in any way?
Inspired? No, I have to say no. I have never actually used just GStreamer in a non-trivial way. Maybe I should have, but also it seems to me that this is obviously how it should work. This is just so clear that there is no discussion about it, right?
I think I agree. It just reminds me very much of you know, in mid-2000s, how GStreamer used to be introduced. This is obviously how it should be. It was also their model. Makes sense.
Yep.
Question about the OPEC pass-through. Is this something that was introduced in 6.0 or it is in the latest?
I'm sorry, what did you ask?
The question about OPEC pass-through.
Yep.
This
I don't remember, honestly. I'm not sure if it's in 6.0. I'll have to check. You can ask me afterwards.
Thank you.
Yep.
I have two questions. One, I noticed you haven't talked about event loops. Is that a natural progression, or is that something completely different in your opinion?
Oh. I don't think with threading you don't really need an event loop, right? You don't strictly speak
Well,
in...
it's Apache versus Nginx.
Hmm?
Your threading design is sort of like Apache, and Nginx arguably changed that paradigm.
As far as I understand, with event loop you would have a main thread that polls and dispatches events, right?
So you could still dispatch those to worker threads.
Yes, you could. That's not what I'm doing.
Okay. And so you're happy is it a natural progression, or do you think that's enough now?
We'll see.
Okay.
I'm not thinking about an event loop yet. Maybe we'll need it, maybe not.
My second question, sorry to be
Yeah, sure.
I think you probably know what this is, but as you know, ref counting lots of small objects is very costly, and I think it's a dependency on your design. How do you think we can solve this challenge?
Well, bundling them into bigger objects,
Yes.
if needed, right? That's
Does the
obvious.
design allow for that?
Not yet, but
Okay.
I think it can in principle.
Okay.
Yes?
What was the most difficult or most painful part of that project?
Most painful?
Like, you had 700 comics for 10,000 lines of code. Why? What was wrong?
Everything. I touched every single line of code in FFmpeg, almost.
Why?
If you diff because you need to move, because of what I said before, the way it was developed is you had some basic design 20 years ago, and then things were just bolted on top of it, and people generally, when they add their new features, they don't think about what effect it will have on future development. So almost nobody actually goes out there of their way to make the code maintainable or extendable or readable or somehow pretty. People think pretty is something extra, something you don't have to do, but I believe it's absolutely necessary if it's to be maintainable. But most people don't think that way, and because of that, the code just rots and it gets into a state that it's not maintainable, and then you have to untangle everything. And that is 700 commits. Yep.
Do you think you'll end up dropping any more niche use cases that were maybe added for dubious reasons? In pursuit of better design.
I actually cannot think of any. No,
I mean,
do you have a specific niche use case in mind?
just in general, you know, you're like multiple hundreds of options.
I'm dropping options. I'm deprecating options all the time, but usually because they are redundant. I just deprecated an option a week ago which is redundant with a filter. So I do that, but we are not losing functionality.
So you should maybe rephrase, like, I've seen things in the FF tools that, like, you know, were added to fix one test case and that's added to Fate?
If that's a valid use case, why not? We should. I do think we should be a universal transcoder. That is a valid valid goal. So covering all the use cases is a valid goal. We might be able to reach that goal without having 200 options, yes. But I don't think we should lose functionality, useful functionality. Yep.
With multi-threaded transcoding pipelines, you obviously need to insert queues between components, but the queues will increase memory consumption. Every queue, if you have 10 components, you will have queue 1 to create an answer. What we're going to deal, how are you going to control the memory consumption? Because it will be obviously much higher.
Right. I don't think memory is really the constraining the bottleneck in most cases. So
I'm thinking, obviously, from video memory, for example, it's more than regular memory, and if you have frames going out of decoder, there's a limited number.
The queues are very small at this point. So and how should I phrase it? The bottleneck is actually interleaving, I think, and you need to buffer for proper interleaving anyway. So I don't think this will add very much.
I'm not saying it's a bad idea. I like the idea in general. I'm saying that you may embed some control over the queues for different use cases.
Right. Well, we'll have to live with that. In what I saw when developing this, is that the most amount of buffering you get is caused by interleaving, by the need to synchronize multiple streams, and for that reason, I don't think the latency added by this should be significant. If it is, we'll see what we can do about it.
With 200 options, what did you test for regressions?
That is a very good question. Well, we have tests. We have tests for many of them. I am adding more tests, but otherwise, we see if users complain, and if nobody complains, then nobody cared.
It's called crowd testing.
No, that's actually that is a test I use for as should I deprecate this option? If it was broken for 10 years and nobody ever complained, then obviously it should be deprecated. It's the right way. Yep.
Is new design better documented than old one?
There is actually a documentation for it. If you look at the mailing list and the patches I sent, the internal APIs are documented, which is just completely, it was never seen before. You know?
Okay, last question. Does it mean that maybe we can now use FFmpeg tools to actually do a complete ABR ladder real time?
Not yet, hopefully soon.
Thank you very much. Welcome to WebEx. Sorry, welcome to Christoph.
So yes, indeed, my name is Christophe Gisquet. So today I'll be talking about AV1 and a slightly bit of WebEx and Cisco. And there's something that I want to be as broad as possible. So I'm preaching to people that are already convinced, but this is recorded and people will watch that video. So sorry if you heard a lot of that, but I think it's very meaningful and very important to mention it. So AV1 is a new video codec that was released in 2018, approximately. People might debate that, but still. So the goal was to have something like a 50% bitrate gain at the same quality compared to H.264. But most importantly, I would say, is that it was meant to be a royalty-free standard from a new organization, AO Media. As a matter of fact, Cisco was a founding member, as well as Mozilla and Google. Nowadays, there are 14 founding status. They were not present, but they decided to contribute, and 30 promoter status members. So I would say that you can ask basic questions like, is there a mobile company? Is there a video streaming company you're thinking of? Then it's likely in that group. And an obvious thing is I might reply or have opinion of things happening, and that's only me. And obviously, there are things in Cisco I don't fully understand, so I'm mostly applying that to myself. So why care about everyone? At this stage, I would say that now it has a pretty strong ecosystem. There are multiple efficient open source encoders. I mean, we have authors right in the room here. Also, we have several decoders that achieve a really good trade-off depending on what you need. And again, we have authors in the room, and thanks again to the David author, so you made AV1 a reality for all of us. I know also of 3 other production encoders, you know, when you want to have some kind of proper control, like bitrate or a real-time encoding complexity. So, and I would say that the next step is about to happen, is that the largest companies you can think of having streaming will at some point soon deploy their hardware encoders to make that an ubiquity and a reality for everyone. I have that number that is pretty old and I should remove because it's now dated and it's not the only user. But at some point, maybe in 2020 or even before, for instance, YouTube already mentioned that they were pushing more than 1 terabyte of data per second of AV1 content. And nowadays, I guess it has blown up, and there are also, for instance, Facebook streaming AV1 data. So really, it's everywhere. And one thing also to consider is that, except a few holdouts, if you look at the mobile market, you look at the people in AO Media, and you look at mobile phone company, 60% of the market is in AO Media. So I would say that the reality is everyone is using AV1, and only a few are standards in that group. And a second thing that was super useful about AV1 is that you have a lot of enablers right at the start of the codec. It's not some strange extensions that nobody worked on or ever deployed. So you have 444 for extreme color fidelity. You have 8 bits. I mean, some companies implemented only 8-bit decoder and noticed that suddenly 10-bit was the most useful thing. And we have all of that mandatory in the decoder. And then we have scalability for those that care. There is also film grain. So really a lot of things that are very useful in a lot of scenarios. So a small bit about how we use AV1 in WebEx. I would say that it's all about collaborative work. We try to address a lot of clients, customers, and basically we have millions of them, and we are streaming billions of hours per year to those clients. So it's very important for the companies that there is no restraint in using those technologies. So it's basically contributing to an open web. And more importantly about video, so you can see real-time, low complexity, and bandwidth savings. So people have much complaints that maybe some of those were not possible with AV1, but actually we can. And AV1 is a huge toolbox. You can use things for real-time, or you can use that for utmost quality. But you can achieve all goals with that codec. For WebEx, The main usage I want to discuss, because it has been in production for a long time, is screen sharing. So we do have some constraints, obviously, because we have to detect that the device is capable of encoding and decoding at a low CPU and battery budget. Otherwise, we don't want to drain the device. And obviously, there are cases where it's not possible. So what we do is transcoding that AV1 content in the cloud, sometimes for interoperability. Again, sometimes you have a device that absolutely can't do AV1. It's just a small power, small device. And another thing is there might be a single user that needs very low quality. So we are not going to downgrade the quality for everyone because of that user. So that's the use case for AV1 in Cisco. I have a figure here on when it was made available. That's the most official one, I would say. But at least in this room, I know someone who was a bit surprised by the date. So the general availability of AV1 in the WebEx client was April 2022. But really, it's quite possible that it was deployed earlier for some particular audiences. And to be fair, it's still a challenge to us to deploy AV1 for main camera video. And the difficulty might not be on the codec side, but it's a whole ecosystem that you have to move with different trade-offs, different things to consider. But that's in the work, and maybe next VDD we'll have good news for you. So really, we are using AV1. Sometimes hard to notice that we are using it. So what happens in some cases when you start sharing your screen is you will see an AV1 logo pop up. To be fair, it has been that for a year, and for most end users, they just see logos that doesn't ring a bell, and sometimes it will, but really it's sometimes confusing. So we are now considering removing it, and it's probably already removed by now, because we have basically finished promoting it. If you are still interested and want to make sure you are using AV1, there is a media statistic window. So I'm not going to explain where to get it, because it really depends on your clients, your versions, the layouts, the OS. So really difficult. And so we have that screen capture where you can see that we are using AV1 in that case. And I also want to point out that for audio, we are also using Opus. I wonder who would use another codec. So really, what I want to discuss now is really why use AV1 for screen content coding. So it's a very, very different content from your usual continuous tone images. So even if you look at this very screen, you see very sharp edges, and it's kind of very repetitive, both in shapes and in colors. And that's something that a lot of codecs did not address well enough in the past. For instance, at the basis of anything related to coding is the discrete cosine transform. So it's very old tech, like it's 30 years, and I mean, in a deployment in a codec, it's even older than that. And I mean, several people have commented on a talk from Yuri Resnick in Demext, which was kind of interesting to track back the history of its usage. In any case, it's all about continuity of the signals. And it's a bit exaggerated, but another point to show that it was not planned to do something else is there is a particular operation called deblocking that tries to smooth out weird effects like blocking artifacts. And what it does is consider discontinuity and error. So really, you have it here. Past codecs were really focusing on things that were not that were continuous. And everyone has tools for that. So I will do a brief presentation of some of those, not in the full details, and we'll skip over some of them. So here you can notice that the main tools are palette and intra-block copy, but there are several tools that are also beneficial. I won't be giving too many details on them. And one thing to consider about those tools is it's really mandatory in any profile and for any conforming decoder, meaning you want to use it, then you're sure that you will get it out on the client. And again, if you want really perfect, better quality, you can use 444 on RGB. That's something that was not possible with H.264 or other codecs that put that in a far away profile. So I don't know if we'll manage to read and see the artifacts here. At some point, I should consider zooming in, sorry. We are using here different encoders, one which is H.264 and AV1, and the context is real-time encoding speed on a very low and tight budget. We are 1 core at most. And you should be able to make out that one picture is a lot worse quality than the other. Text is blurry, you hardly can read some of those letters. So you have quite a better quality. But AV1 also achieved that at 40% of the bandwidth. So that's huge. That's a game changer. So tools. So I had to mention that tool because I really like those kind of tools. It's Chroma from Luma, from people in the room again. So it starts from the fact that in video codecs, we usually transform from RGB to some more perceptual color space, YUV, YCBCR. I mean, the fact is, it was used to try to decorrelate information, put as many details for the human eye into the Luma. But as you can see, we would think, okay, we are done with processing chroma, or I mean color. But actually, what you see is there are still shapes you can make out in the color pictures. And that's basically what that tool is exploiting. It says that if you look at Luma, you can guess a bit of what the chroma is. So you do a fine transform on the Luma channel. You have to transmit parameters, but that's all you have to do for that, and you have a much better reconstruction than regular intra-prediction. And it can be used actually in more than screen content coding as soon as you have something rather colorful and with strong edges, like, I don't know, video gaming. It will be a tool that has a major role in gaining a bit of bitrate. I would rank it at approximately 5% bitrate gain, but that's just a ballpark. So, intra-block copy. Well, I guess with that we are done. I guess we can call it a day and finish the presentation here. Except we are codec guys, so we like to make things complex. So, block copy. I mean, people have worked in FFmpeg here, have known specific codecs doing that. It's, I mean, the most obvious temporal prediction we've been using in the past. It's maybe 40 years old. I would say that if we look back to some standards, motion vector at some point was an oddity. And looking back to what can do block copy, there was this specific codec, JBIC2, used in some faxes and scanners that was already using intra-block copy. And that's a standard that is maybe now 20 years old. If you start at the very basis of that tool, it's quite easily a 10% bitrate saving on an intra-image. That's kind of critical because you don't often achieve that amount of saving, and has a boatload of consequences like delay, things like that. And To be fair, that's just a conservative number. I've seen 40–50% gains easily on intra-images. And again, I'd say it's 40 years old tech, but you have to take into account that there is hardware at some point. So I'm not really an old hardware guy, and so I'm trying to paraphrase what's happening there. Is usually you build that stuff in separate blocks, which are pipeline. You can see that as kind of a waterfall. The output of the stage goes into the other, and they are somewhat separated. You don't like to introduce the dependency between those. And as a consequence, for instance, intra-block copy in AV1 isn't allowed to use the latest block decoded in the regular order. So those are in yellow here. If you are trying to decode the green block here, you are forbidden to use the 4 preceding yellow blocks that were decoded just before. What you are allowed to use are the violet blocks here. And again, there is a particular rule to that. You can see some kind of staircase shape. That's because there are interdependency between the line. You are using data from each other, and sometimes it's difficult to synchronize those things across. So that's a way to decrease the dependency between the different steps in the decoding. And I would say that many codecs have similar constraints and way to cope with those dependencies. And by the way, I mentioned block copy. Well, what is it about? So it's block matching, basically. You have something you want to predict from a past observation. So it's another block, basically. And what you do is try to find the most similar one by some means, like computing the difference and so on. And then what you do is transmit the displacement, the coordinates of the other block that offers the most similarity. And on top of that, you will transmit additional information. So block copy using motion estimation. That's a thing that I want to point out is that while the techniques used in those tools are sometimes known for a long time, a few details might be very interesting, but really at the heart of those, it's mostly about encoders methods. So hash motion estimation, I would say, is historically kind of a very old technique, but it was used mostly for images. So what you would do is you compute some kind of gradient map over a block, you try to synthesize it, quantize the data in it, and you come up with some kind of feature code, and that's what you will use as matching. So you won't look at the pixel data, you will look at the representative code, the features of the block instead. And what makes it very efficient is on text. Text, as I said, is very repetitive. So you will actually have a very few hashes. I mean, still a number of them, but a lot less than in continuous tone images. And this technique has been probably used now for at least 15 years for codecs that try to code screen content. And one way of doing it is actually using not really a hash, but something that is close to, which is a cyclic redundancy check, which is now an instruction that is available in a lot of CPU. So you can have some kind of summary of the block in a very cheap way, meaning you don't need to derive those gradients, which are actually costly. And this makes it practical to sum up the block in that way. So what you do is you have a particular block size, let's say 8 by 8, so it's 64 bytes, and you can generate some kind of representative code with CRC. And so what you do afterwards is you compute that over the reference data, and you just look up the block in a table that matches that CRC. So it's extremely efficient. It can speed up an encoder, and it can result in big bitrate savings. And that's really what matters for that technique. You can use regular motion estimation, but you won't get as good results. So palette coding. So
question about your block copy.
Yeah.
Yeah. What percentage of blocks in a frame end up being block copy?
So if you speak about AV1, it's restricted to intra frames, and it's really dependent on the content, but we can probably achieve 50% of blocks. I mean, that's not an unusual number. So palette coding, where is it used? So when you look again at that screen, you can see that basically there's only a few colors, like there's bright blue, darker blue, and so on. So we've been designing UI elements with faster means, so usually they have to be sharp, readable, and they don't use that many colors. If you look at some screens, for instance, a spreadsheet application, really what you have is some background color and the color of the text, mostly. And you could maintain that legibility with only 2 colors. And if you move to 4 colors, you have some of the sub-pixel renderings that is mostly okay. So you get back the smoothness in the letters. And palette coding, again, is a very old technique. I mean, GIF, pick your poison, is one such image format that used palette a long time ago. PNG also use that. And I would rate such a tool as 15% bitrate saving easily. I mean, you can be very exhaustive in what you do with that and achieve more, or you can achieve less if there is a complexity trade-off. And what it does is basically reducing the number of colors in an image. So for instance, you can see here on the right an 8-color palette. So it still looks like a regular palette, but it only has 8 colors. So meaning that it's not only text, but sometimes you can use reduce elements to have fewer colors. And the actual use case is mostly for letters, again, when you never noticed it. So that's an actual capture of a letter in that presentation. So we have some kind of letter, and we want to say it's only using 4 colors. So let's say we have 4 colors that are representative, the most similar to the color in the letter. So you will look in the table what's the most similar color, and use the index as the representation of the pixel. So you build a table of indices, and that's what you are coding. And again, on decoding, you pick the color in the table and represent the pixel with that color. So, I mean, in FFmpeg, there's plenty of that. But again, the real challenge is the encoder. So how many colors to use? So the AV1 also decided that 8 colors should be enough for everyone. That's not the first time we've heard such things. But here we are in a particular scenario, which is coding. So with 8 colors, you achieve the best quality probably. But the issue is if you use as many colors, you will have a lot of overhead. More signaling, larger indices to signal, and so on. You will increase the bitrate. So you have to find a trade-off between the number of colors and the bitrate that you produce. To be simplistic, I would classify the methods in 2 categories. One is your usual histogram of colors, and you look at the histogram and find picks. Those are the important colors. Those are the 4 colors you were seeing previously. And obviously there are other colors, but they are pretty rare, so you can discard them. Another method that is used in a few places is classical clustering methods, k-means, and there are plenty of variation around that topic. So what you do is try to gather similar colors, and you have a group, you compute the centroid, kind of the weighted average of that group, and if you have a pixel that you want to code, you look how far you are to that group, measure the distance, and maybe you need to signal another color. So again, you can iterate over that to have the best summary of all colors in the block. So as a conclusion, I would say that the thing to take away from that is in everyone from the most basic profile, meaning that it's available everywhere. We have plenty of tools in everyone to address screen content coding and achieve, as I said, easily a 30–50% bitrate saving on screen content with a lot of benefits. I mean, you can be a lot faster than H.264 and save a lot of bandwidth. And I would say that it might appear theoretical, academical, but it's a daily usage that can be achieved. So really, it's the reality of everyone for screen content. So that's it. I can take question.
How good are screen coding tools from everyone compared to HPC and VDD?
I would be hard-pressed to give an exact number. I would say, however good they are on the paper, you have to implement them. And at the end of the day, you might not be using all of the feature of a format. And I mean, it would not be a decision factor. Which codec has the best gains here? Yes?
How much information are you giving the encoder about the content? So in this case, if it's screen recording, you're telling the encoder, I'm doing screen recording, use all the features around RGB,
Yeah.
etc.
So you can detect that. That's what most encoders would do. Sometimes some encoders do a bad job at it, some encoders are better.
Is that expensive? Or like, do you save a lot of compute costs?
So to be fair, indeed, using those tools has a cost, in particular for block copy. I mean, you're doing kind of motion estimation. So it's a different one, so it has a cost. So it's better to properly detect the parts where you can skip it, indeed. Yeah?
Do you think the codec that succeeds AV1 will be based on neural nets?
Okay, real time. So, yeah, no, but I mean, at least in the context of WebEx, we have to have a very low CPU budget. Plus, it's screen content, so you want real time. So, neural networks, I haven't seen them used for screen content coding.
Reply in 4 minutes when your neural network is done.
Sorry, what?
Reply in 4 minutes when you answered the question with your neural network.
Yeah, maybe. Yeah.
Are you streaming full to zero or 4 WebEx? Because like for Excel spreadsheet streaming, for example, and also the hinting of Windows, which you have lots of artifacts before to zero. So how do you address that?
So it's kind of a difficult question because a lot of processing relies on 420. We have use cases for 444, but they are kind of higher end of the spectrum. So that's a part where I don't really know when it's activated and who benefits from it. Yeah.
How much do you use hardware encoders, and if you do, they use very well all the tools you mentioned, or it's very sketchy?
So hardware encoders, they are starting to become available, but that's a specific devices. I mean, we are trying to address such a wide ecosystem. I mean, that's your phone, that's your laptop from 5 years ago, things like that. So hardware encoders are a possibility, but at some point you will still need a software encoder.
Yeah, it's a question about that selection of the palette. I imagine there's a lot of potential there to get a lot of compression, right?
Yeah.
It depends quite a lot on your ability to do that automatically with the choice of your clustering algorithm.
Yeah.
So you don't standardize the clustering algorithm that you use, right?
You standardize?
Any sort of clustering algorithm, K-means is one, means a whole bunch of other stuff.
Yeah, so I mean, that's a part where I mean, there can be encoder algorithms that are pretty smart, and it's not the best idea sometimes to share them. I would say that the real issue is you can be pretty good, but you have to balance it with the complexity. So K-means, in particular, if you're going to be iterative, are pretty expensive. So I would say it's sometimes a bad idea to use them, actually.
So I can't remember, are the palettes, when you encode the palettes, are they entropy coded?
Yes, and that's a big part of the AV1 standard, and there's probably some benefit to it, but I mean, I don't want to start to mention context-dependent entropy coding and what are the fine details of the palette. For instance, there's a particular scan order to help our decoders, but I mean, that's not what makes AV1 efficient. It is efficient because of it, but it's not a game changer.
Thank you. Miraculously, we're on time. You have a 20-minute break. There is coffee just outside. Please be here at 11:09, so we can start at 11:10. Rémi? T'es le suivant et c'est ça. C'est ça?
Ouais.
Good.
Gauche et droite?
Ouais.
You get an external dependency which is lib whatever. Yeah, there's also you should never should not underestimate the program that whenever you say that a certain person there is that.
Go away for 100 milliseconds. That's what happens to do any sleep in the frame.
Yeah, that's big. Yeah, like the event loops we see a lot aren't necessarily big things. So it's the case network things go into the given person's event loops rather than that. It's in it when you see a lot. That's true. Just wouldn't need it. Just put other things in their own press and bottom.
Yeah, that's right.
Yeah. Well, it's stopping.
Why do you have
No, I mean, not many people do. Yeah.
Yeah, if you want to cover all calls, but what I do is, I don't do anything fancy, I just do plain, simple YAV, nothing fancy, no YAV, no HDR. And
I guess if you have a very well-defined use case that doesn't change much.
Yeah, we actually have most of what you do is really low latency, like pseudo transcoding for those. So for those you really don't want to have that Yeah, of course it's more like interacting with it, because how do you, when you spawn it, let's say, how do you interact with it, how do you control it, how do you...
Like, right, illustrates.
Fuck's sake. No, but actually the practicality is that if we are forced with, in a non-real-time scenario to deal with an HDR file, we do actually these days a bit probing, check that if this HDR is something funky, I don't want to touch any baby filter, so then I just spawn an FFmpeg.c.
So you have a firewall for human filter?
Yeah, pretty much. Because I don't want to...
Where you are writing a program, where you have a use case which has basically a fixed pipeline and doesn't have any of the variability libraries, because that is the right way to do it.
Yeah, but
once anything's dynamic, or you need the AV filter because the AV filter is horrifying.
It depends on how much of the what a decoder can do you want to cover.
Because all the speakers were like inching closer and closer.
Can I do a quick fix here? Just need to reduce this guy.
Non. Non. C'est interdit de manger dans la...
You want to turn this on, color mic, do you want?
C'est marqué, ils n'ont pas de...
Oui, mais ça fait genre, t'as plein de monde à ton truc, tu vois. Voilà.
Ouais, mais je m'en fous, non.
Do you want this color mic?
If you think I should use it?
It was fine without that, right? You was able to hear, I was able to hear from back, so it should be okay. If you want, you could use that as giving an option. Okay, so if you are within this area, this is fine. If you are beyond this place, color mic is needed.
Alright, no problem.
Alright.
Folks, it's time to come and to sit and start again. Ça te va?
Ouais.
2.
Hein?
Parle fort.
Ouais,
Ton
ouais.
micro est là. T'es enregistré.
Ah, on est 5 minutes en retard. All right. Well, I guess we are screwing the ones who didn't come back. Welcome to my presentation on my own behalf, I suppose. Yes, so I'm going to introduce RISC-V or RV and the RISC-V vectors. And if you think it repeats too much what I said at FOSDEM, complain to Kiran. And if you think it doesn't repeat enough what I said at FOSDEM, you can go and watch the talk on the FOSDEM video site. So what is this about? And first, so yes, before we go into that, this is just a weird hobby, it's not my work. But regardless, all the everything I say is just my opinion. So how do you get an x86 processors nowadays? So, well, there's two ways you can get an x86 processors. The first option is to buy it from Intel Inside, or Intel Corp. And the second option is to buy it from AMD. Yeah, good luck trying to make one yourself, even if you are like Apple and you have like, I don't know, many billions in the bank. If you try to make an x86 CPU, you'll be taken to court for patent violation, and that's not going to end very well for you. So the only option is to buy hardware from one of these two companies who have cross-licensed their patents. How do you get an ARM processor? Well, there's basically three options here. So you can buy it from one of the ARM licenses. Or you can go to ARM and ask them for a blueprint for one of their IP, so one of their Cortex CPU, presumably, and then you can try to get it fabricated yourself or by factories that make CPUs. That's going to be quite expensive. Or you can get a license on the whole ARM architecture. But, well, yeah, if you're less than $1 billion company, you don't need to apply for that.
Isn't there a fourth one called B Apple?
Yeah, so Apple is a category 3. Apple actually bought an architectural license, but Apple has $1 billion, so they can do that. And NVIDIA also.
All the architecture versions.
Hmm?
They get all the architecture versions.
It's possible, yeah. I don't think you can buy all of the versions, but I mean, NVIDIA also has one. I suppose Amazon has one. I don't know. Yes, that's not very good. So for RISC-V, well, of course you can buy it from one of the vendors. And there's many vendors, many more, I think, than ARM even. Or you can license a blueprint from one of the vendors, like Sci-Fi or Andes. Or you can just download a free design on the internet. Or you can just design it yourself. Now, admittedly, as a single person, you might have a difficulty designing a hypervisor cloud CPU, but a microcontroller, you can probably do it yourself. And this is the thing, right? RISC-V is patent-free. It's an open standard. Anybody can implement it. It's all about choice. So what RISC-V is not, though, and I mean, this should be obvious for most people here, but I think sometimes there's some confusion. RISC-V is not a processor. It's an instruction set that is implemented by many processors. It's not an operating system. You can use Linux. You can use FreeBSD. You can use a bunch of other operating systems if you want with it, and it's not a tool chain. Of course, Clang and GCC support it, but people get confused a lot. And unlike ARM and x86 and most other popular instruction sets, it's not proprietary, and it's not, or at least it's presumably not patent encumbered. What it is, well, an instruction set. It's an assembler syntax, which goes with being an instruction set. It's also a non-profit standard organization, RISC-V International, or RVI, which is nowadays based in Switzerland for geopolitical reasons. And it's a baseline instruction set for 32-bit microcontrollers, which is usually abbreviated RV32I, and a lot of standard extensions on top of it, and reserved space in the instruction set for your custom instructions if you want to write a custom CPU with custom things, like DSP functionality, for instance. So, extensions. So RISC-V is a very scalable ISA, and by that it means that you can implement a very small CPU with it, and you can implement a very, very big CPU with it. So on top of the RV32I, you have RV64, which is a 64-bit support, RV128, which, as you can guess, is a 128-bit support, of which there is no implementation except, I think the only implementation is actually a simulator made by none other than Fabrice Bellard. Then you have, for instance, M, which is multiplication and division, because that's not part of the base specification, because RISC-V scales down, and you can have very small microcontrollers that don't want to have multiplication. Multiplication, if you remember how to do it in binary, it's much, much more complicated than addition, so you can remove that. Atomic ops, which of course you typically want on a multiprocessing system, and a floating point, so you have FD and Q for single, double, quadruple. Well, quite usually you have all of I, M, F, AD, so that's G is general purpose. That's what you usually work with when you do FFmpeg stuff or VLC stuff. So general purpose application processor will have, well, it will have obviously multiplication, atomics, and floating point. C is compressed instruction for cache optimization mostly. And then the alphabet soup goes on. B, bit manipulations like counting zeros and such. H is virtualization. P is packed SIMD, like ARMv6 SIMD style. You don't need to remember all of this, obviously. There's also A, J, and T, and then V is what we're most interested in today and in multimedia talks, which is vectors. So they still have K, N, O, R, U, W, and Y free if you need to make a custom extension. So all the stuff in S is for supervisor stuff, and it's other letters after that. SV is for virtual memory in particular. X is for vendor-specific extension, kind of like, you know, Java and ManyUser or MIME extensions. And Z is for the standard new extensions for which there's no latest, that there's no free space anymore. So, yes, that's the end of the alphabet soup. So why is it called RISC-V? Well, RISC obviously means reduced instruction set computer. So it should be a rather asynchronous reduced instruction set architecture, but anyway. So this is the instruction format if you actually like look at the binary, if you actually open the RISC-V spec and look at how to encode certain instructions. And as you can see here, so it's a 32-bit instruction set. The bottom 2 bits are always 1-1, that's for instruction variable length coding. And you have 7 bits for the opcode, which is like the general category of instruction, like you'll have load, store, arithmetic, branching, and so on and so forth. And what you see is that the other stuff is also always in the same place. So RD is a destination register, and you can have at most 1 destination register. So in the most generic case, you'll have up to 3 source registers, RS1, RS2, RS3, and 1 destination register, RD. Each of them have 5 bits. Now, this is very rare that you actually have 3 input operands. Usually, you only have 2 or even only 1. But this is the most generic case. And then if those aren't necessary for your instruction, then the extra space is going to be freed for other additional function distinctions or sub-functions, sub-opcodes of sort, or then as immediate values if your instruction has some immediate parameter in it, like add 1, add 2, add 3, and so forth. And why is it done this way? Well, it's because decoding instruction on a real CPU takes transistors. And generally speaking, you have a certain budget of transistors that you have for your CPU, and you want to be as efficient as possible, and you'd rather dedicate. If you have free space on your die, you want to put it to useful stuff like 1 more ALU, or some extra vector capacity. You don't want to put it to like complex decoding, instruction decoding. You don't want to do like what x86 does, where they have a sizable chunk of the processor just dedicated to decoding the input instructions. And I mean, seriously, now it's a trend to implement your own RISC-V simulator in C. You can do that in less than 1,000 lines. Good luck doing a 1,000-line emulator for ARM, and forget about doing a 1,000-line emulator for x86. I mean, I know because I've done it. So yeah, operands are always in the same place if they're there anyway. It's extremely easy to decode both for hardware and for simulators. And that also means it's easy to pipeline and reorder. And if you have a more advanced CPU like superscalar CPU or out-of-order execution CPU, it's much easier for the pipeline to see where the data dependencies between different instructions are going to be because, well, the input and output operands are always in the same place. And that also means that it's much cheaper to implement this kind of more advanced features that you will find on like more powerful CPUs like you would typically find nowadays on a application engine like a mobile phone, a computer, a laptop, or a server CPU. Of course, as is typical also in RISC architectures, and if you've done ARM or MIPS, I mean ARMv8, or if you've studied MIPS, you will recognize it, is that we use and abuse the 0 register. So there's 5 bits per CPU. It means we have 2 power 5, 32 registers possible, and of course one of them is a 0 register and actually has number 0, not number 31 as it has, because of course that's much more logical, but anyway. So there's of course convenience instructions, so instructions that don't actually exist, but you will see them in code, and that also means that it's simpler to decode. It doesn't make sense for a human being, but for the computer it does make sense. So for instance, load immediate, which is just putting a fixed constant inside a register, is actually adding 0 and then the constant. And copying a value from one register to another register is adding 0 to one register. And bitwise negation is just doing a XOR with -1. Negation, arithmetic negation is subtracting 0 from the value. And even that gets weirder, and maybe like you wouldn't think about it, even the jump instructions are actually using the 0 register, because in RISC-V, for simplification reason, the jump register and the call register, the jump instruction and the call instructions are the same. And the destination operand is basically the return address register. So if you don't want a return address, if you don't want to save the return address, then you just put 0 as destination operand. And this gives you like a return instruction which doesn't look like it doesn't have any parameter, but it's actually a jump and link register with 0 as a destination, and then the return address register as input, which is called RA. So yeah, let's come to the more interesting things for this audience. The vector extension. Yeah, you can see it's a bigger section because it has subsections. Some background, and here we're going to repeat a bit what we said in FOSDEM, but so here's an oversimplified summary of SIMD on x86. I hope everybody knows what SIMD is. Does somebody not know? Yeah, so just to be clear, SIMD is when you do the same operation over multiple inputs at the same time, and that's also called, well, single instruction, multiple data, that's what it's called. It's also called vectors because you just process, well, like when you do linear algebra, you might do sum of vectors, multiplication of vectors, whatever. So anyway, on x86 in 1997, you had MMX, which was the first, not the first vector implementation, but the first one on generally available CPUs and not on massive scale machines. And then you had 128-bit because, of course, 64-bit wasn't enough. With SSE, which had many revisions, SSE2, SSE3, and then SSE4, and SSE4.1, and SSE4.2, and SSE4A, and yeah. And then they realized that this was a mess, and Intel came up with AVX, which is still 128 bits, so it doesn't really do much anything better, but anyway, it's just coded better. And then they realized that, well, maybe we need more, so there was AVX2 on 256-bit in 2011, and that was still not enough, so they came up with AVX 512 in 2013, but that was only on some weird CPU, so it really only came out in 2017, and then I suppose you could talk to some people in this room to know that this was actually never really working fine, but so anyway, you gotta love rewriting your inner loops, because, and I mean, I didn't even put the list of the SSE variants, so I don't know how many times, and I didn't put 3D now also, so yeah. So it kind of sucks to have a fixed size vector for your instruction set. And Intel finally realized this, and they came up, I guess, just like a month ago with AVX10, which will actually have kind of, well, basically will be the AVX 512 encoding, but with variable size vectors. So how do you deal with variable size vectors, though? Because now that the variable size, you need to write your code in such a way that it will work with different vector size on different machines. So when we say variable size, of course, we mean across machines. Of course, within a runtime, you're going to have a fixed size. So the plain dumb approach is to just ask the CPU what is the vector size. So in RISC-V, you do a control and status register read instruction, CSRR, of the VLAN B register, which is a system register, constant in this case, which tells you how many bytes there is in a vector. And then if you want to say operate on float, on single precision float, you need to divide by 4 because you have 32 bits. You want to convert to number of elements from bytes. You can do that. That's what, at least the initial automatic vectorization on RISC-V, and I think also on SVE, on ARM, from LLVM did. It's not the smartest way to do it, but it works. So you write your main loop, then you unroll your main loop, and then you deal with the edges. And just like in the good old days. Yeah, it works. It's a very bad way to do it, but a second approach is to use vector masking, or yes, so that's a bit more flexible. Here you introduce yet another set of vectors in addition to your regular vector registers that contain your actual data that you're being processing. You add a bunch of mask vectors, which are basically a set of booleans, which is one boolean per element in normal data vectors. And with that mask, you can say that for each instruction that you have, you can say like which elements in the vector are active, which means that if it's a load instruction, they will be loaded from memory. And if it's a store instruction, they will be stored into memory. And if it's just a computational instruction, like add, multiply, shift, whatever, they will be modified. And if they are masked, so they're inactive, then they will not be modified in the vector. And AVX 512 did introduce that also for fixed size vectors, so it's not a new idea. Also, ARM SVE has it. It's not, of course, it's ARM, so they have to rename everything. So it's not called mask, it's called predicates, but it's the same principle. And And you can use this, I mean, of course, you don't typically use this kind of feature intuitively in multimedia use cases because you don't typically mask elements, but you can use this to count down elements as well. So you just say, as long as my vector is smaller than the amount of element I still have, I will not mask anything, and I will process everything to the fastest, to the full size of the vector. And when I get to the edge, I will mask the end, the tail of the vector, because now my vector is now bigger than the amount of elements I still have. So that's why it's a bit more flexible. With that said, you also have one extra complexity here, and that's a masking policy. So at least in RISC-V, we have two masking policies, which is how to deal with inactive elements, so those elements that are masked. So the undisturbed policy is that inactive elements must be preserved by the CPU. It's potentially a little bit more expensive. And the preferable one is the agnostic policy, which is saying that I don't actually care about what's inside the vectors for the inactive elements. You can just corrupt them however you want, and this is potentially faster. So this is something to keep in mind. Usually you can work with agnostic, but there are a few algorithms like scalar product, for instance, where you do need to use undisturbed. Yeah, the third approach, which is the simplest, in my opinion, and that's the one I recommend using all the time, is working with the available vector lengths. It's kind of a variant on the masking approach, and it's only available on RISC-V. It's not available on x86 as far as I know, and definitely not available on ARM. So it comes in addition, it's orthogonal to the masking in practice, is to just tell the CPU however many elements in your vectors you have. And this looks like this. You have, well, this is our first, well, not our first, but our first vector instruction here. So vector set, vector length. So here A4 is our register which contain how many elements we still have. And T0 is the destination, operand is output. It's the CPU will, after executing this instruction, will tell us how many elements it will process. And of course you have parameters here, so E16 just tells the CPU that we are working on 16-bit elements in this case. We'll see what the other parameters are in the next slide. Because of course, vector size is fixed in number of bits, so the number of elements you can process in one iteration is, or in one instruction is dependent on the size of the elements. Now, be careful, it's not the same as a max, as a min instruction, so it's not always. So let's say that the vector size is 128 bits, so you have 16 bytes. So if we would here use 16-bit elements, we would have 8 elements in a vector. If you have, say, 10 elements, so if A4 is equal to 10 and we still have 10 elements to process, and you use this instruction, T0 will not necessarily be 8. The specs, to be accurate, it says that it must be at least more than half of the vector size. So it will be at least 4, but so essentially it says that it can't increase, the instruction can't increase the number of loop iterations you have to do, but it doesn't have to be the max all the time. So don't assume it's the max, because this is not going to work. At least not on all CPUs. Yeah, so the other parameters, as I just said, the element size, as you would expect, it can be 8, 16, 32, or 64 bits. The multiplier, so here it's 1, which means there's no multiplier, times 1. It can be anywhere from 1/8 to 8 times in power of 2, so 1/8, 1/4, 1/2, 1, 2, 4, 8 vectors. It's essentially how many vectors we are dealing with at a time, and I will get into a little bit more about this again on the next slide. And then tail mode and mask mode, so again, agnostic and undisturbed, which I mentioned earlier. So in this case, we are using A for agnostic, you have U for undisturbed, for both the tail mode and the masking mode, which is the most common situation. So, yeah, unrolling. So if you've written SIMD code before, most likely you have had to unroll to get the max performance out of the CPU, and most classically you will unroll with a factor of 2, but sometimes even 4, depending on the loop and also on the register pressure you have on your inner loop. So, well, on RISC-V, as I said, we have 32 registers, and this is because the instruction format is fixed, regardless of the type of register we're dealing with, whether it's general purpose registers, vectors, or float registers, it's always 32 registers. If your loop has less than half of 32 registers, so if it has less than 16 registers, then you could unroll twice, and if it has 4, you could unroll 4 times, and the same as on every other architecture, of course. So, yeah, on RISC-V, it's actually done usually a bit differently, is that instead of actually unrolling the code and then repeating the instructions with just different register numbers in the flow and just basically doubling the code size and then adding an extra loop, an extra iteration without unrolling at the end to deal with the edge, in RISC-V, what you do is you just tell during the vector configuration, which we just saw before, the multiplier. And if you say, for instance, M2, it means that instead of having 32 registers, you'll have 16 registers, but they will be double the length. And the way this works is that you can only use then the even numbered registers, so V0, V2, V4, until V30. And then you can do this again with 4, then you have 8 quadruple size registers. So if we had 128-bit registers, then suddenly we will have, instead of having 32 128-bit registers, we'll have 8 512-bit registers, so almost AVX. Except we have, of course, only 8 registers instead of 32. And you can even do it with 8, and then you have, of course, only 4 registers, which means that, well, only the simplest algorithms can possibly be implemented, but they will be octuple size. Now, it doesn't mean that it will be 8 times faster. Of course, it's down then to your CPU pipeline, how many units it has to actually do the calculations, but this allows for unrolling in a very efficient way for the programmer. And also, generally speaking, you just want to maximize. So you just, once you've written your loop, you just see how many vectors you need, what's the register pressure, and you just put the maximum multipliers that you can do with this loop. And you don't have to be, oh no, I'm not going to do it times 4 because it's just too much work. Like, in this case, it's just changing one letter in your assembler loop, so it's extremely easy. So edge handling, well, edge handling sucks, and especially when you have to deal with alignment. So usually on vectors, you have to align to the size of the vector when you do load and store, especially from memory. And imagine now doing this with runtime variable, well, with a runtime determined alignment, which is not fixed at compile time. That's going to be really hard. But fortunately, we don't actually need to do that. On RISC-V, the alignment for the memory operations, so loads and store transfers, is the element size. So if you say 16-bit elements, then you just have to align your input and outputs on 16 bits, or 2 bytes. So yeah, no more edge handling. Like literally, you don't need edge handling because even if you have one element at the end, you just iterate the loop with just one element. So this is an example taken from the FFmpeg, actual FFmpeg code. Of course, I added the comments here. And this is the simplest I could find, but this is actually a functional unrolled RISC-V loop from FFmpeg. And this just computes the product of 2 vectors. So we set the length. Here A3 is the third argument register, so it contains the number of elements in the vectors. And we use 8 as the maximum multiplier available because we only need really 2 vectors, so we can multiply by 8 here, no problem. So we load one register into V16. We load another register. And we load one vector into V16, we load another vector into V24. And then VF-mul VV is vector-vector multiplication, so we multiply one vector with the other and put it back into V16. And then we store the result. And then the adds and subs are just to adjust the counter register and the pointers. So you just, yeah, SH2 add is adding one value multiplied by 4, shifted by 2, because we are dealing with floating points and single position floating point, which is 4 bytes. So of course our pointers need to shift by 4 times the element size every time. And then once you've done that, you just have loop until the counter A3 is 0, and once if not the case, you just restart the loop, and if it is the case, then you just return. And that's it. So I don't know any other architecture where you could, well, maybe PowerPC, but definitely not ARM or x86 where you could do a functional optimized loop and so few lines of code. Yeah, so what are the actual vector lengths? So today you can already find on Alibaba, an Alibaba design. Alibaba the shop, the Alibaba the IP, the CPU design company, 128 bits. They have been designed and announced from various vendors. for 256, 512, and even 1 kilobit. I'm aware that there are some actual simulations, like theoretical design on the schematics that have up to 4 kilobit. I don't know if we're going to see that big in a real production, because at some point the industrial trade-offs start making no sense. But in theory, you could do with the syntax of the instruction set up to 64 kilobit. But I would expect that pretty soon we're going to see larger than 128-bit. But one important thing with variable vector lengths is also that different lengths make more or less sense depending on what type of product we're dealing with. So certainly on a mobile device, we are never going to see 512, because it just doesn't make sense to dedicate so much of your die on a CPU, on a mobile CPU, for just vector instructions, because you don't do that much vector processing on a mobile device. And it costs a lot of money to have a big vector, because you need to store those vectors in system RAM and so on. And that's why it makes a lot of sense to have variable vector length instruction sets. So that's it. If you want further reference, of course, the unprivileged instruction set architecture specification and the vector extension specification, and of course you can also peruse FFmpeg source code. Questions? Yes.
So previously there were issues with hardware availability for these vector instructions in their final form. Has this improved during the last few months?
Yeah, so there's at least one vendor, I think it's called Canaan, which has a standard conforming vector implementation today. The product, I think, has really just released, so it might not be like, maybe not today, maybe today you can't buy it on Alibaba, but I expect that within a month you can buy it on Alibaba and get it delivered to your home by post. Yes?
You mentioned that there's multiple different element sizes that are supported.
Yeah.
You said, I think, 8, 16, 32, 64.
Yeah.
Is there also support for smaller, like 4 bits
No.
offerings, for
No.
example?
So there are reservations for larger. So it's a power of 2. It's included as a power of 2. There are reservations for larger sizes. So I think up to 1 extra bit. So you have 2 power 7 would be the maximum. 2 power 7 bytes would be the maximum. Whether it's going to happen, probably not. But you can't do sub-octet sizes. Of course, there aren't that many algorithms where you do with 4 bits values anymore. So there is a vector.
I think machine learning these days, they want to use 4-bit vectors even if it's faster.
Yeah, I mean, because I guess like machine learning is also a lot of 16-bit float. That's not currently supported, but I expect we'll see some extensions for that, because we can do 16-bit values, of course. There is also vector crypto extension, which has things like vector XOR and kind of things where you can do bitwise ops, which you can't do in the base spec. Yes. Yeah.
Yeah. So this implementation specific, but has the element size an impact on the throughput or the energy consumption?
Yeah, it depends on the design, because.
But for those that you know.
Well, I'm not working for a design company, so I don't actually have exact details. But I do expect that, generally speaking, some instructions will be tied to the number of elements and not to the element size, because, for instance, if you take add, it's probably going to be that you have a certain number of adder or arithmetic logical unit in your CPU, and whether it's 8-bit elements, 16-bit elements, 32-bit elements, it's not going to matter. You still have to do the addition one by one, because you can't parallelize it, right? So I think it will not so much, well, to some extent depend on the design, but it will also depend on the instruction. Because obviously the load and stores are not going to be affected by the number of the element size. But then
so I'm working on a project to run RISC-V on the blockchain, and obviously you don't want to do, well, it sounds crazy, and it would be to do RISC-V general in Solidity, so we're doing RISC-V-I in Solidity and then doing an emulator. What sort of slowdown would you see emulating vector instructions on RISC-V-I?
It's going to be a little bit slower than just not using vectors in practice, because you'll have a little bit more of like management overhead. Like if you pretend to have vectors and you really don't have them, It's not going to be much slower than doing scalar, but it's still going to be slower than just doing the scalar algorithm. Yes?
Is anybody implementing quad precision floats?
Not that I know. not that I know, but it's in the spec. This is like 128 bit.
Power 9 had none.
Yeah.
In order to get access to the lunch, you need to write one assembly function for FFmpeg in the next 45 minutes for all of you. Okay, thank you very much. Oups. Toi, t'es quoi? T'es un PDF ou t'es un... Nicolas.
Hello everyone, and thank you a lot, not only for being here, but also for building tools that allow to play multimedia. But at the end of the day, all of your hard work has to be made available for the end user. So that's what we are going to talk today. Is the example of VLC for Android. So my name is Nicolas Pompuy. I'm the VLC for Android lead developer. I'm also a Video Lab member and a Video Labs employee. So let's talk quickly about VLC for Android. The current version is 3.5.4. It uses VLC 3. The next versions will be 3.6 and 4.0. The 3.6 version will include a way to favorite all the medias and media lists and so on, but also a web server that we will talk about later. About the platforms that are supported, you can run the Android app on Android, obviously, on the Android TV, Chrome OS, and Windows with support for Android application. In terms of distribution, we distribute the app on the Play Store, on F-Droid, but also on the Videoland website, Amazon App Store, and so on. We currently have 60 million plus active users, but it's only counted for the Play Store, so it's probably much more than that. So this is an oversimplified preview of the app architecture. On the left side, we have multiple Kotlin modules that are used to do all the functional stuff and for the UI. And on the right side, you have our main dependencies, which are obviously libVLC and the media library. So let's talk about libVLC GNI. So libVLC GNI is a Java project. It's built using Gradle, which is a build tool, and it includes multiple things. It includes, of course, the GNI binding, which make it possible for Java code to talk with native code. And it also has some data classes and helper classes to be able to directly create a player that can work really easily without having to do too much work. It can be used in two ways, either as a Gradle module or an AR dependency. We will talk about that later also. It also includes the US scripts of VLC, which are included directly in the Android assets. At runtime, it's then copied
in a dedicated folder, and it can be used that way at runtime. So about the VLC for Android Kotlin project, there are different Gradle modules, and we have a lot of them. It has some benefits. It can improve. It improves the compilation time, because when you do a change in a module, you will only compile this one. Also, it improves the cleanliness of the code, because you can cleanly separate the different features. And also, it allows us to release some of our libraries on Maven as AR artifacts. So here is a list of all the modules we use. I won't describe each one, but we have some functional ones, some mainly the VLC for Android one, which has all the mobile UI, the player, and so on. We also have one for television, and so on, some utilities, DB management modules, and so on. And the two last ones are libVLC and the media library. About the compilation, VLC for Android can be compiled in two ways, either with a building script or directly with Gradle. So let's see the difference. If you build it with a compile script, it will retrieve all the libVLC GNI and VLC code through a Git clone. It will then compile all the C, C++, and so on code, for example. That's the same exact thing for libVLC and the media library. Then, when all the native code is built, it will use Gradle to compile the Kotlin project and to bind the native library and in the application. So there are some pros and some cons. The pros is that you do a native compilation, so you can test a change in the C code directly. Also, you can split by CPU architecture, so have different APK file for different CPU architecture. It's used by the CI, so that's the way we are testing our merge requests. And it's also versatile, because there are a lot of params, for example, to avoid rebuilding the patches and so on. But the cons are that the compilation time is increased a lot. For example, to start to compile one CPU architecture on my machine from scratch, it's around 10 minutes. And it can be launched directly by Android Studios, so you cannot debug that really easily. So the other way to do that is to compile directly with Gradle. So when you compile that way, it will use libVLC and media library AAR artifacts, so pre-compiled versions of the libraries. And then it will also build all the modules using Gradle. So you will have a better compilation time. It will be done in seconds instead of minutes. And then you can launch it directly with Android Studio and have access to all of the development tools. But in the cons, it will generate really large APKs with all of the architecture included, so more than 100 megabytes files. And you cannot do native changes and see them right away. So what about this AR artifact that I'm talking about since the beginning? In fact,
to make it really easy for apps to use libVLC or the media library, we are providing some artifacts through Maven. So an AA artifact is the exact same thing as a jar, but with the support for Android resources. And then when you want to create a project that is needed to do some multimedia playback, you just have to add the first line. And then in 10 lines of Kotlin code, you are able to spawn a media player and start playing video files. To do an artifact release, here's our process. We just have to create a tag and push it on GitLab. Then the CI sees this tag, starts the build of the artifacts themselves in parallel build, so it's not too long. And then we just have to sign this and push it to Maven Central. So then it's available for everybody that wants to use it. And it's more or less the same way for the app release. We create a tag, push it, and then the APKs are built by the CI. We download it, sign it, and then we have a tool which is called Fastlane, and which allows us to publish it on every store we want. We can also, with Fastlane, publish the screenshots and so on. In the next version of VLC for Android, we will add a new feature, which is a web server. This feature will be really useful for our user. We are asked a lot to do that. So if you have your VLC for Android instance on one device, you want to be able to control it. Maybe you don't have a remote controller, or for other reason you want to access it with another device. So in the next version, VLC for Android will include a HTTP server using the Ktor library. And then using your web browser, you will be able to completely control your VLC Android instance with it. So it will look that way. So that's a website. That's not an app. That's the website you get when you connect to your other Android device. And you can control, for example, the playback, but also navigate through your media library and start playback. So to do that, we had to add another building process. So we have a Vue project, which is a JavaScript project, and you can run two different commands to run it. At the bottom, you can run serve, and it spawns a local server, so you are able to debug it right away, make a change in the JavaScript file, and the website is reloaded, and you can see right away what you did. Or you can build it for release, and then all the website is copied in the VLC for Android assets, and at runtime it's extracted to be used by Ktor. That's about it. Do you have any questions?
Why is Gradle such a piece of shit? And why did we not, after now 15 years of Android, find a new system, right? Like Google every 3 years change it, so why have they not changed it again?
When Google decided to go from Eclipse to IntelliJ and provided Android Studio, the tool that was used for all the Java projects was Gradle. in IntelliJ, so they decided to go with it. They are trying to actively make them move forward, but it's still a pain. It's written in Groovy, which nobody knows about. But they are pushing things in the right way, in my opinion, because now you can use directly Kotlin files for the build description. We didn't move to that for now, but we will probably. Yes?
What's coming in version 4?
It's not a secret. There is a merge request opened. Mainly VLC4, so a lot of tests, more tests, and also more tests, because it will probably break everything. We are working right now in an instrumented test suite to be able to test VLC4 on multiple Android devices and test for regressions and so on. The main features that will be seen by the user will be a new tab in the app allowing to use external sources for media, especially podcasts in the first version.
Why do you need a web UI to control your device when probably there's some people doing some low latency remote control streaming?
Because sometimes you don't have network. But like, the good question is, why do we need that now? And the answer is that Android, every version of Android is locking more and more the Android system, and it's getting closer to an iOS thing. While at the opposite, now it's getting easier to access files on iOS, right? Because now you have a file browser on iOS. Right? But Android is every version of Android. And the thing is, as you probably have seen or not seen, Android is now pushing the deprecation. Like, you cannot maintain an app at all anymore unless you have the minimum API version. So you need to target the new version, and as soon as you start the targeting of the new version, then you'll get fucked because you have the new behavior of the old codes. Right? So it's getting very difficult, and for example, it's a problem for us because we still, if you have an old device, we still have the old APK, and those are going to be disabled by Google. Right? So
not the old APK, they will remain. Even if it was not clear at the time, the old APKs will remain, but each time we do a new release, we have to increase the API level to be the higher possible. And when we do that, we get the new restrictions. We were really lucky to get a special permission that nobody have access to, except us and a really small portion of the apps, which allows us to have access to the whole file system. And that way we can have access to files that are not considered as media by Android themselves, by the system itself. For example, to rip zip file, we can't get them directly if we don't have this permission because it's not considered a media by Android. So we are still lucky, but it's a pain more and more a pain to work with that on Android.
In which sense are those special permissions special? Does like Android system check that it's
No. You can use it, but you can distribute your app. In fact, you can't have this permission and be on the Play Store. Your app will be rejected at the publication time because you have this permission and you are not whitelisted by Google. So you can always create your APK, put it on your website and distribute it. There are no problem with that, and you will have access to all the files, but you won't be able to do it on the Play Store.
Okay, thank you. So we have another talk, heretic talk from people using Google Slides instead of using proper LaTeX. You've seen that we put both of them at the end on purpose. Thank you, Ronald.
All right. And that one works, right? Yes. Okay. So. Sorry? Say again?
Auto mic in the table if you want.
Oh, yes. Yeah, that's probably better. Does this work?
Yeah, you need to turn on the top.
Yeah. Yes.
Oh, yeah. Is that better?
I think so, yes. It's just because my throat is a bit sore, so then I can talk softer, but you can still hear me. All right, so I would like to give you a status update on David. You should know what David is, right? David is an AV1 decoder. It's a video LAN project, so we're all friendly with it here. And most of the introduction can probably be skipped, but I want to show off assembly, I want to show off threading, and I want to mostly just show off code that is in David and what makes David, in our opinion, a great AV1 decoder. At the end, I'll show some performance analysis of David also, both compared to other AV1 decoders to the extent that they exist, and then also compared to the code complexity versus other codecs, right? So how complex is AV1 if you compare it to HEVC or VP9 or 264? We can put a number on that, and we're going to try to do that. Okay, so very briefly, David was introduced not in Dublin, but at VDD in 2018. That was me there, like at the bottom. Is there a pointer? No. Help? No.
At the top there's a pointer, the red icon.
Yes. How do I turn it on?
You touch it and it uses it there.
Oh, there. Yes. Okay. So that one is me, and that one is Jean-Baptiste, and I was already old here, but I was a little bit younger. That was cool. Back then, what I showed off was just a C version of the decoder, but it was mostly already bit-stream compliant. The goal of David, as stated back then, and I think it's still the goal today, is be an awesome software decoder for as long as we need one. Because we don't actually want a software decoder, we all just want hardware decoders, right? And for those nerds out here that think that we work with software and we do video processing, mostly we just care about video to watch Netflix on a TV or you know, to watch an Instagram clip on our phone. Right? Like when I ask my parents, how do you consume video, they think consume is a weird word, but they actually watch TV at night. They really do. And when I ask my wife, how do you consume video, she actually watches things on her phone all the time. The way that we look at like writing a software decoder is weird for them. They just want it to work on their phone, and they just want it to work on their TV. And most of the time they use hardware decoders for that. But there's a problem, right, where if you have a new video format, it doesn't exist. So how do you make a new format popular? You write a software decoder. You use it for as long as it's necessary, and then eventually hardware decoders will come on their way and we will become irrelevant, and that's okay. So we're not there yet, so we still have a reason to exist, so where are we now? I think the best way to describe David is to look at our source code. Our source code mostly consists of assembly. It's about 150,000 lines of code. If I remember correctly, Jean-Baptiste said that that's more than an FFmpeg. Is it more?
It's 220 now, and it's a lot more than the rest of the FFmpeg.
So this is a lie, don't believe me. I do believe that the 30,000 lines of code of C code is actually correct, right? And so it's mostly just assembly, right? So because it's mostly assembly, when I introduce David, I have to mostly talk assembly, right? So what kind of assembly exists in David? We have SSE3 assembly. That's for very old desktop laptop systems that are like 20 years ago, maybe even older. If you look at something like the Valve software store, they give you statistics on how many, what are the capabilities of each system that is connected to our store. They say that every single person has SSE3.
if you look at Chrome, they actually only run on SSSE3 and higher machines. Right, so we can assume that everyone has that. You don't need to target lower than that. We also support 32-bit. I don't know why we do that. You should not use 32-bit x86 systems today, but it works.
Could you break down these 80% by architecture?
Yes, I will do that later. So yes, there is a slide for that, but it's not this one. Okay, then if you have a computer that is about 10 years old, it will support AVX2 most likely. We support that also. And then if you have a very new system, you're unlikely to have one of those today, but it might support Ice Lake or Tiger Lake are the newest chipsets from Intel. They have even more special instruction sets, and we have coverage for that also. Not all functions are implemented, but I have some slides on that later also. Then if you have a phone or something else, it's an ARM machine, and we have assembly for that too. These percentages are sort of made up, but basically what it comes down to is that for SSSE3, we support everything except 12-bit inverse transforms and self-guided filter. And you might be like, why didn't you write them? Because nobody cares, so we're not going to do them. Okay. Then for AVX2, we support, again, everything except that someone in this room decided to write 12-bit transforms, because why not? So it's not 95%, but I don't think there's anyone actually using that. Then this is the AVX512 status. This is confusing, so his fault. He can fix it by writing more of it, and he's actually working on that. I think the relevant missing features in this list are the directional intrapredictors, which are these for 8-bit content, and they are here for 10-bit content. And Hendrik is currently putting up merge requests to fix that. The other things that are unchecked here, right, so for example, something like stop working. Directional interprediction. The directional detection of the CEDA filter. We'll probably not implement those because they operate on very small block sizes, and AVX512, one of the main advantages is that you get bigger registers, and so there are not actually any gains associated with using AVX512. So this will probably mostly stay the way it is, and that's okay, because it's not like it falls back to C, right? If the function missing is missing, then it falls back to the AVX2 version. This is the ARM status. This looks different, because Martin didn't like the way that we presented our checkmark list for x86, so he did it differently. I think this is essentially the same. Like you can see here that for 32 bits, the directional intrapredictors are also missing, right? So this is the Z123 that we were just talking about. Skilled motion compensation is missing. And I assume, oh yeah, and 12-bit, of course, is missing because we hate 12-bit, right? Only for the self-guided filter. For the inverse transform, it's just that the container size needs to be bigger. Okay, so talked enough about like the general status of the code. So I want to give some examples of what makes David great. Now, David is mostly written in assembly, so I'm going to have to show you assembly, because otherwise I can't prove it, right? It wouldn't be representative. All right, so I'm going to start with inverse transforms. What is an inverse transform? Think of an inverse transform as a math function that you don't have to understand and you don't have to know, but it's something that operates on a list of numbers. And because video happens to be two-dimensional, right? It has like a width and a height. The transform is also a two-dimensional thing. So we can decompose those. So we can have a one-dimensional transform, and we can do that in two different directions, and then that gives you the two-dimensional transform. So if David did have C code, which it doesn't, but if it did, the inverse transform would be written like this, right? So there is a size, which in the AV1 case can be something like 4, 8, 16, 32. There's a type, which can be DST, ADST, or identity, or Philip ADST. All those things you don't have to worry about, because they don't actually matter for what I'll talk about next, right? Think of them as like, I don't know what they do math functions. And then you operate on a list of numbers with that math function. Now, David is written in assembly, so not that one, this one. So the typical implementation for an assembly function for that same thing would look like this. This is exactly the same as what you just saw for the C version. And this is actually the implementation that you will find in libaom today. So we do the same thing, but because for the horizontal transform, the data that you want to operate on are right next to each other, which conflicts with how SIMD typically operates, right? So in SIMD, we want the data that we operate to be distinct for each other, and then to be the multiple data units to be next to each other. So that's not how it works for horizontal transforms. So to fix that, we do a transpose. So you transpose your data, you do your 1D transform, then you untranspose it, which is the same as a transpose, and then you do the vertical transform, and then, right, again, the now transformed residual can be added to the predictor, and that's your final block. So this is pseudocode, but this is literally what libaom does. And this is a good implementation, right? This is how I would write it too if I were a college student or so. Because there's issues with this, right? So C functions are designed in such a way that they have an ABI. And the ABI in C functions is that if I have an array of data, then that array of data needs to be written back to memory at the end of that function, right? That is the expectation of that function. And then when I call another function, it will have to load that data back out again. So when you look at the disassembly of that function that I just showed, most of the runtime is not actually in the one-dimensional transform anymore, which I didn't define because it honestly doesn't matter what it does. Most of the runtime is in loading data and saving data and loading constants and then splatting constants across your whole register. And there's all these things that we thought the compiler would take care of for us, but it doesn't because C doesn't work that way. And no C++ doesn't either. And no Rust doesn't either. So, okay, so there are better implementations of inverse transforms. This is how it works in GAV1. And the relevant difference here is that the transpose is integrated in the one-dimensional transform. Right, so the one-dimensional transform is, it looks roughly like this. What a transpose, it's not just that it's inlines, but the data types are actually like stay within the scope of that function. And because of that, the function understands that I don't have to write that out to memory in between the transpose and the actual one-dimensional transform implementation. The disadvantage of that is because that thing is now inlined, it means that you need two versions of the one-dimensional transform. One horizontal, which includes the transpose times 2, and a vertical one, which doesn't. And so your code size doubles, which is a problem. Because Chrome, for example, doesn't like shipping huge binaries, right? Just try adding 10 KB of binary size to Chrome. You will be hard vetoed. It's just not a thing. Also, this fixes the loading and saving of data after and before the transpose, but there's many other cases where we still do it. And I'll show detailed numbers on that later. But just for now, remember that conceptually, that is a problem. And that is where most of the runtime is actually spent, not in the actual math, which is what we would like to spend most of our runtime on. All right, how do we fix that? So David is written in assembly with a thin layer of C, so we solve that by abusing assembly. So this is Martin's code, and Martin is very clever, so he does little tricks, right, where he comes up with his own ABI for a function where it says, my registers are filled with this data, and they just stay there when I call another function. So here we take the address of a particular one-dimensional transform, and you go to x5 and x4, and then I say, call this function. And then I call this two-dimensional wrapper function, and that we load the data once, and then we call the one-dimensional transform, and then we call rounding or a transpose, or we call the other one-dimensional function. And note that we never actually stored the data. In assembly, you have to actually tell it what to do, right? We never told it to store it back to the stack. We also never told it to load it back from the stack because we're entering a new C function. Because we don't have to. We can make up our own calling interface. And the transform, which I never talk about, is just a bunch of multiplies and additions then. And that helps a lot. No, yes, this one. So how much does that help? So if you look at the disassembly of each of these functions, and then you classify for each instruction of that function, what does that thing do? For David, the actual transform, just the multiplies, additions, and shifts, are 2/3 of the total cycle of the total instructions in this function. And the remainder is things like, well, I actually have to transpose, or I actually have to add it to the predictor, and then write it out to get your final block reconstruction. This is a sensible implementation. This is how you want it to be. This is what efficiency looks like. Now, for GAV1, you can see that most of the time is spent saving data to stack, loading data from stack. Also, a lot of constant loading, which I don't really understand. Like each constant that they load takes them 3 or 4 instructions, which is weird. I don't think that's necessary, right? But that's how they do it. There's also a lot of branch control and loop counters for things that don't actually loop, but they write a for loop anyway because it's pretty, and then it takes many instructions. And in the end, you can see that the instruction count is approximately double. Now, for something that is double the amount of instructions, it will not surprise you that it is twice as slow, and that's indeed what we see. It's not that they're bad at writing Neon, it's just that if you use intrinsics, this is what happens if you don't specifically tell it to do otherwise, right? Intrinsics aren't magic. They just can make it easier. They can help a developer if you know what you're doing. This is not just a Neon problem, right? For x86, they have the same problem. So there's an additional issue on x86, which is that they only have SSE4 assembly. For those not aware, SSE4 is for systems that are, again, 20 years old. So it's kind of ancient and slow and doesn't have a lot of instructions for like advanced things that we'd like to do. But, so we support SSE3, right, because 20-year-old systems are a thing. And yeah, here too, we're about almost twice as fast, depending on the transform size that you're looking at. And then we also have AVX2 and David, which again adds 2x on top of that. That's the actual speed that you get from the inverse transforms. That difference is big enough that SVT AV1, for example, uses the David inverse transforms, not the right. It mostly uses libAOM code, but here they specifically integrated the David inverse transforms because it probably gave them a measurable benefit. All right, other assembly. So let's talk about film gray now. So this is an example where x86 is particularly cool. I don't think what I'm going to show here is possible on Neon just yet, but it's okay, maybe one day. So film grain synthesis is synthetically created grain that you can overlay on top of your on top of your otherwise reconstructed frame, and then you get a nice old movie effect. The actual implementation, right, ignoring things like overlap and chroma and stuff like that, it's essentially a loop that looks like this, where you have an addition and a multiply, and there's this shift, which I didn't show, and there's a lookup. And this lookup is something that is very difficult to do in SIMD, because there are no obvious instructions for that. So this is what an SSSE3 implementation looks like. Not sure how many of you can read very old assembly, but basically the idea of SIMD is that I have an instruction and it operates on a vector of data, and it does that for all of these elements in that vector at once. For example, I have a multiply, and now it multiplies like all 16 of them all at once. So what this code instead does, and this is not a joke, is I extract the first 2 elements from my SIMD register to a general purpose register, right, 2 at a time. Then I split them in 2, and then I do a lookup for each of them individually, and I insert them back into a different register. Then I do that for number 3 and 4 and 5 and 6 and 7 and 8 also. And it probably won't surprise you that because this is actually a 16 element register, that I only showed you half of the code. So the etc. here is that I actually repeat this twice, and then I've operated 1 lookup on 1 register worth of data. So this is fake SIMD. This is not real SIMD, because there's no way to do this in SIMD. This is for 1 register worth of elements, so for 16 pixels. This is 46 instructions, or almost 3 instructions per pixel, also known as very slow. AVX2 gives us a gather instruction, which I think Neon doesn't have, right? So this is a little bit better. Yes?
I believe this instruction has had a security advisory recently. Is that right? Down, I think it's down 4 or something. Have you measured,
Yes.
Have you measured the
we've not measured the impact of that yet, but I did read that. It's one of those funny things where I guess if you're worried about your security, then don't let other people on your system. And boohoo for Amazon. Oh well. But yeah, it might have an impact on this. I think they did say it would get twice as slow, the gather instruction specifically, yes. That's a big deal for workloads that include this instruction, yes. Okay, so going back. So AVX2 gives you a gather instruction, and a gather instruction means I can do a lookup in memory, but lookup is on at 4-byte resolution units, right? So if I have a register that has 1-byte units, I first need to convert them to 4-byte units, and then call, right, because that multiplies the amount of registers I have with 4 also. So I need to then do a gather on each of those registers and merge them back together. And so this is what it looks like. If you do that, you so it's already split at the beginning of the loop here in 2 registers. There's xmem0 and, or sorry, ymem0 and 1. And here I filter out the even elements and the odd elements. I do a gather on each of them, and then the blend merges them back together. So this is the destination. You have 4 and 2, and 4, 2 are merged back into 2 here. Then you do the same thing for the other one, where you take the even entries, the odd entries, you do the gathers on them in 3 and 5, and you merge them back together in 3. So this is 14 instructions for the same thing. These registers are also twice as wide. So 32 elements, 14 instructions, about 0.5 instructions per pixel, right? That's a lot better than 3. And so this is faster. Now, AVX512 is awesome because you can actually do this. So a pixel in 8 bits has values from 0 to 255. So you would do an 8-bit lookup. In AVX512, your registers are 64-byte wide, and there's instructions to do a shuffle between two registers, which means that you have 7-bit indexing space. So if you do 2 of those, you have 8-bit indexing space, and you can do the lookup, but all within registers, never accessing any memory. And so that's what you do here. You load your table in init code once, and then you do a permute on the first half, on the second half, and you blend them together. And now 5 instructions, and you've done the exact same thing that with SSSE3 cost you 50 instructions. And your register is 4 times as wide, so you did 4 times as much work. What is the runtime impact of this? It's like this. So SSSE3 is, as you would expect, slow. AVX2 is about twice as fast. This is normal. AVX2 tends to give you about almost a 2x speed up on top of SSSE3. But this is not normal. So normally the speed up from AVX2 to AVX512 for a single function is about 1.3. In this case, it's 3x because we have good instructions to do what we want to do. And that's really exciting. So yay, Intel. Okay, so there was a question just now, how much for each instruction set is there? So this slide is meant to answer that question. So we have SSSE3, it's about 65,000 lines of code, AVX2, 50,000 lines of code, AVX512, 35,000 lines of code, and then 30 to 35 for ARM, one for 32-bit and one for 64-bit. For ARM, that's comparable to what libgAV has, GAV1, and for x86, it's a lot more. The interesting thing, though, is because we have so much fewer C code, and C code tends to, compile to much bigger binary size than assembly. The binary size is actually very favorable for us. So for x86, the binary size is about the same between GAV1 and David, and for ARM, we're actually significantly smaller. And that has nothing to do with this, but all to do with this. It's because David is not written in C. David is written in assembly. Okay. Talking about something different, right? So we want to talk a little bit higher level stuff. So let's talk about threading. So one of the big performance improvements that we've seen in David more recently that is not assembly related is our threading implementation. So classically speaking, like if you look at FFmpeg or libvpx or old versions of libaom, their threading typically works in one of 2 ways. One example of threading is tile threading, which means I have an image, I split it in 2 halves, I just assume that those two have nothing to do with each other, and then I decode each of them separately, just as if they were two images instead of one. And then at the end, if I want to do things like a D-block post filter, I just wait for both of them to finish, and then I do these things that cannot be split as two separated workloads. Then this is FFmpeg's typical threading model is frame-based threading, which means I have one frame, I have a second frame, and I just decode both of them together, right? If you have intra-only content, that's super easy. For inter-content, it's a little bit more tricky because the motion vector from frame 2 to frame 1 might actually rely on this block already having finished decoding, and so this one sometimes have to wait. For this one. So that means that your frame threads are typically not at the same vertical space, right? So you have a delay between in the progress of your different frames, and that also sort of gives you a cap on how many frames can be active or what kind of concurrency you can expect from this kind of multi-threading, right? And that's the case for tile threading also, because not everything can be tile threaded. So in the end, these threading models, maybe you can keep 2 cores, like 3/4 active, or 4 cores a little bit active with a bunch of threads. It works, but it's not perfect. So I'll show you some data later on why that wasn't good enough for David. And so in David, we decided to do something else, which I think we call it a task threading. It's basically, rather than having threads do work or do nothing if there's nothing to do, we have worker threads and a list of tasks that they might possibly execute, and then they just pick from that task list one by one as they see fit. And that can be anything, right? So you don't have to have a thread that does a frame or a thread that does a tile, but a frame can be a task and a tile can be a task, and that thread will just pick that task as it sees appropriate and just do what it can. So the best way to look at this is just to look at what kind of tasks are available. So you need an init task, because we're object-oriented, I guess, and we like having paper overhead. The reason that you need an init task is because in AV1, frames rely on the entropy data of previous frames. And a task list entry has dependencies associated with it. And so this is how we can tell it to wait for that previous frame's entropy state to be available before you start processing this frame. Then after that, you go into bitstream reading, which is 1 task per tile. Then separately from that, you can do bitstream or block reconstruction, right, which is the prediction and the inverse transforms. Again, 1 task per tile. And then after that, you have each of the post filters, 1 task per post filter. And I'm pretending here that it's dblock, cdef, and restoration. I believe dblock is actually 2 tasks, right? 1 for dblock in that direction and 1 for dblock in that direction. And there's also a film grain task, which I didn't show here because I didn't have enough space. And then the dependencies basically resolve all of this thing. So if a dependency is met, it means I can execute that task. If a dependency is not met, I just leave it in the queue, and as a worker thread, I just pick some other task to work on instead. Is this better? Well, let's look at some performance data. So this is on a mobile phone, on a Samsung Galaxy S8. And blue is David, red is GAV1. Assembly-wise, the best way to look at the assembly performance between the two is to look at the single-threaded performance, so that's always the leftmost point. Differences, it seems small here, but the difference, like the baseline is actually very low, right? So the difference is about 10, maybe 15%, depending on the content. Is that right, Martin? That's what you see also? Yes. So that's a substantial, 10% is a big deal. But the real killer here is the threading, right? So you can see here when you have 4 threads active, and both of them are pretty good at keeping more than 3.5 cores active with 4 threads. But this difference is no longer 10%. This difference is almost 50%, I think. So you can see that the threading model scales much better for David than it does for GAV1. Yes, Kieran?
Are you able to elaborate a little bit on what the threading model is like in GAV1? Is it more like an older style? Or?
So I believe that it uses tile-based threading, but so that's what I get from reading the code, but I'm not 100% convinced that that's actually true, because they scale a lot better than I would expect with tile-based threading alone, or than we saw with tile-based threading alone. So there may be some other piece of magic in GAV1 that I don't yet understand. So I don't want to absolutely confirm that. The x86 threading data is more consistent with what I would expect to see with typical tile-based threading, which, again, I think is what they're using from reading the code, but yeah, with an asterisk. Yeah. Okay. So for x86, I have to split it in two because we have multiple instruction set that we support as well as threading. So first, let's look at the instruction set impacts on decoding performance. This is all single-threaded. This is high-definition content, right? This is 10-bit, 4K, and 12 frames a second. Might not seem much, but again, this is single-threaded, right? And this is 4K, and this is 10-bit. So this is a lot of frame data. So even with SSSE3, you can get 12.5 frames a second, whereas for GAV1, you get half of that, right? But that's a big difference. And then once you get to AVX2, so the problem with GAV1 is it has some AVX2, but not that much. And so you would expect then that the impact of AVX2 is small, which it is. For us, like AVX2 was the default that we based everything on, and so you get to 20 FPS already. You get another almost 10% from AVX 512. That's better than what most people see. Most people, when they use AVX 512, they don't see any gains at all. So this is a good thing. It's not 2x, but it's good. And then threading, so this is the same story as what you saw for ARM. We clearly scale better than this other encoder. And here, the threading model problem that I talked about comes into play, where you have 4 threads, but you keep less than 3 cores active with GAV1. So one core is, it gets work assigned to it, it just doesn't know what to do with it because there's no work to do. For us, this is 395%. So you have 4 threads, you keep 4 cores fully active, which is how it should be. That is resource efficient. Okay, lastly, do I have 5 more minutes, JB? No, well, I'm going to do it anyway. So I'll do it in 1 minute. So how does this compare to other codecs? So the way to do that is you don't have a single file anymore. So you have to encode multiple versions of the same file, either at the same bitrate or at the same quality. I did the second one. This is the encoders that I used. This is the settings that I used. This is the PSNR that I got out of it. I tuned all of them for PSNR. And this was the decode performance. Blue is David. And so the points are 1, 2, 4, and 8 threads. This is how many cores were actually active for that thread count. And this is the decoding speed in FPS. And this is for 1080p instead of 4K. So the FPS is a little bit higher. You can see the code complexity-wise for the same quality. David basically accomplishes the same performance per core usage as HEVC. And then this, for comparison, is VP9 and H.264, which we know from previous work are roughly equal as well. Then SVT-AV1 has a special flag where you can optimize for faster decoding performance. This is how we enable that, and so this is the file that we selected. And if you do that, then the complexity of AV1 is the same as 264, but the threading scales much better, not just than HEVC VP9, but even than 264. And also with VP9 here, you can see the classical problem of threading models when you have entropy dependencies between frames, where threading just doesn't help that much. And that's why we changed our threading model to begin with. Is anyone using this? I think so. Not sure. Like, there's companies and browsers. And, I think some people use it. Ask them. But none of this matters because there's hardware decoders now. So I don't know why we did all this work. Seems kind of pointless. Okay. But there's still work to be done, right? I mentioned directional intra-prediction. Kyle put up a patch for CDEF and block stripes, which improves the performance of CDEF a lot. I think Jean-Baptiste wants to do a lot of work in GPU acceleration. There's all these new instruction sets like RISC-V and all this new work to be done. So it never ends, and then we'll go to AV2. These are the kids that actually did all this work. They're amazing. Buy them beer, and thank you.
So we are late on the schedule, so no questions. Question will be asked during lunch at Ronald. If you want to eat, we are doing a photo now, right? So if you don't go to the photo, you don't eat. Just jokes aside, we go for a photo right now, just before lunch. Everyone, now.
Like it?
Yes, very grateful.
How can you be sure that Apple will implement properly in hardware?
I don't want to think about it, but I love your question. Yes.
Yes. So exactly, that's what I said. So get a message.
VLC don't have phone, VLC people are poor.
Il faut savoir que Trinity, c'est un lieu de visite, c'est un musée qui est ouvert à tout le monde, n'importe qui rentre.
Du coup, tu as une meilleure suggestion pour stocker nos valises?
Bah non. Bah là, tout de suite, pas vraiment, mais moi, ça me donne.
Attends, si, on peut le foutre dans la régie?
Quelle régie?
Ça. Le truc derrière.
Ah ouais, j'ai pas les clés. Faudrait demander à John. Tu vois qui c'est, John?
Non. Je vais demander à boutique de quelqu'un.
Oui, je sais que c'est John. Comment ça qui est cassé? La lanière, elle a lâché. La fermeture éclair, elle a lâché aussi. Ah, regarde.
Tu peux l'amener chez un cordonnier, tu vas pas.
Ça peut coûter 600 balles, même pas tenu un an. Parce que chez The Couples, les seules choses qu'ils avaient, c'était en terre.
We need to lock this room now.
Yeah, but we would like to know where to leave the luggage, you know?
No, we lock this room so it should be fine.
Okay.
He'll open it after the lunch.
Oh, everything is locked?
So we can lock this now and take photo and come back.
So I can leave my stuff here.